Okay, what we're going to do is continue in Chapter 2. We're going to look at our measure of position. And so position really has some different features we can look at. We're going to look at quartiles, which are dividing our data into 4 groups with equal amounts of data in each group. And the boundary of those groupings kind of give a shape to the data. We're going to look at other percentiles and how we can find those percentiles. And then we're going to look at something called the Z-score, which ties back into the standard deviation. So a quartile is a type of fractile, which is where we divide the data into partitions or fractions, that each set has an equal number of data elements in them. So for a quartile, we divide our set into 4 equal parts. About 1/4 of the data is below the first quartile. Half of the data is below the second quartile, which is the same as the median, and 3/4 of the data is below the third quartile. So we're going to look at this example, and I'm going to do it graphically, and then we're going to do it in Excel. And so if we look at this data set here, what they've been able to do is they've taken 15 cities with urban areas where people sit in traffic, and they look at how much gasoline people waste per year in these cities. And ordering the data in order, the quartiles, if I look at my median in the second quartile, if I count 7 over on each side, the median gets centered out. That leaves 7 pieces of data on either side. And the median of the first side is the first quartile. And the median of the second side is that third quartile. And so it's the art of taking successive medians. And so what we can do then is we can process and we say, well, 1/4 of the people lie within the first quartile, half the people lie within the median, 1/4 of the people lie between the first and the second quartile, and so on. And so this gives a shape to the data. Well, let's look at how we can do this in Excel. So let me get over to my Excel mapping here. I've already put the data in place. And one of the first things I do when I have data like this is I come to the Data tab up above, and I go to Sort, and I'll sort it from smallest to largest. Now, Excel has a quartile function. The one we're going to want to use is quartile.exe. And that's exclusive. So what this will do is if I take B2 to B16, which selects all my data, and then here I'm going to put a comma, and I want the first quartile. So comma 1. So this is the first, whoops, cancel. First quartile. Now the second quartile is the same as the median, but I'll use the quartile command also. So I'll go quartile exe, because we want it to be exclusive, B12 to B16, and second quartile. And notice it's telling me here what the percentage of the data on either side is. And now we'll add the third quartile into place. And so again, B2 to B16 with the colon. Oops, B16, I typed a 15 in there. And we'll want the third quartile. What did I type in wrong? B2 to B16. Did I type something wrong in here? Let's see here. Let me retype this in. Oh yeah, I didn't type the word quartile, and I just typed quart. B2 to B16, comma 3. And now I have the boundaries of the 3 quartiles, of the inside boundaries of the quartiles themselves. So Excel can make this calculation easier for us. One of the things that happens if we lose or we have even values, we'll sometimes get that averaging that we saw with the median. And so we're going to look at some examples of that as we come across. But at least Excel gives us a way that we can find our quartiles in our data. And very shortly, we're going to look at what that means when we go to plot these. And so, 1/4 of the people in large or urban areas waste less than 26 gallons of fuel. And about halfway, 31 gallons or less, and 3/4 waste 35 gallons or less. And so that's what the interquartile range does for us. Now, what we want to do then is we want to put a measure to what quartiles are, and it's called the interquartile range, because 50% of the data is going to be between the third and the first quartile. So it's a way of kind of looking for a clump in the center. And so what we can do, because we've set this up in Excel, is I can take my interquartile range here, and I'm going to call it my IQR, and that is going to be equal, well, it's our third quartile, so that's cell D4, minus our first quartile, D2. And that tells us that 50% of the data spreads out over 9 gallons difference. And so it's a way of talking about, how wide this data gets spread in the middle 15%. So the interquartile range is a good way of talking about how the data has been spread about. And so this formula, IQR, is the third quartile's position minus the first quartile's position. Now, what we can do is we can use this to find outliers in data. We can take whatever that outlier may be with that interquartile range, and say if our data gets further than the endpoints, that might be an outlier. It might not be clumped in the center. So what we want to do here is we want to multiply the IQR by 1.5, and then subtract that from Q1 and add it to Q3. So what we're doing is we're making a boundary that says this stuff is further away than the center is clumped together. So let's do that here. We'll make our outliers. And so we'll do 1.5 IQR. So I want to take 1.5 and I want to multiply it by D5. And then what we can say is that if you're less than this value, so it asked us to subtract this from Q1. So we'll say equal, and we'll put the cell for Q1 minus G2. And so that's saying data values less than 12.5 are probably an outlier. And if you're greater than a value, you're probably an outlier. And that asked us to take the third quartile. So we go equal C or B4. Right, not B4. Our third quartile is D4. I'll learn my alphabet someday. Minus or plus G2 and 48.5. So this is telling us if we get data values below 12.5 or data values above 48.5, they're probably outliers. They're probably pushing the mean away from the true value, just like we saw graphically in the last chapter. And so having this interquartile range gives us a means that we can get for calculating this. And let me redo those calculations since the slide's stuck here. So I'm going to delete this and redisplay it on the screen here. So what we're going to say is we're going to use that formula and we'll look for outliers. So the thing we want to calculate is the 1.5 times the interquartile range. And so our interquartile range is D5 here. So we're going to take 1.5 times cell D5. And so outliers that numbers that are smaller than C2 minus this 1.5 IQR, which we're hiding in G2 here. D2, keep doing C's for D's. So things less than 12.5 would be an outlier. And then greater than, that would be equal to D4 plus G2. And so we use this spread here to determine boundaries of things that just might not fit our data. Sorry about the flipping screens here. Let's see if I can get back to the PowerPoint here. But at least we have the tools to calculate this quickly in our spreadsheets. Well, what this lets us do is set up a box and whisker plot, which is generally called a 5-number summary. And the 5 numbers that we need is the minimum entry, the maximum entry, where the first quartile is, where the third quartile is, and what the median value is. These 5 numbers let us plot how the data is falling over the range. So I'm going to plot one by hand, and then we're going to see how Excel does this. So I'm coming over here to my Blackboard, and we'll look at our data here. We need the minimum value that we had, which was 24. So we start a number line that could have all our possible data values on it. And we start at 24. And then we go to our maximum value, which was 39. So 39. And then in, let's see, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. So that's a better way of plotting that. We'll make 39 here, 38, and this is 36. So we have a number line with all of our values listed out. And what we want to do is we want to mark where the first quartile came, which was at 26. So we'll put a big line here. And our second quartile began, our first quartile is at 26, and our third quartile boundary is at 35 here. So we encase that in a box because 50% of our data is in this box. And then we highlight with a whisker everything out to the minimum value. And so this is called a whisker and box plot, or a box and whisker plot. And so you highlight where 50% of the data is, how wide it is, and how the tails are. In fact, looking at this, knowing that 50% of our data is here and it has a tail, a longer tail on the right, we can see it's right skewed. And I would think that the distribution probably looks something like that if we were to compare it to the distributions we had before. It's definitely shorter on this side and longer on this side, with most of our data falling in this range. Well, luckily, Excel has a quick way for us to do this, though it displays it, I would say, slightly odd for us here. Let's come into Excel, and I'm going to select the data I want to look at. So I click on these cells here, and I'm going to go up to Insert, and I'm going to come to this particular icon, which is Insert Statistics Chart. And I come down and I choose Box and Whisker. And here it has created one, but it's running vertically on it. So we kind of have to read these going up. And so there's the 24 with the small whisker on it, my big box in the middle that is 50%, and the small whisker coming out. And so we have the ability now to do a box and whisker plot that gives us a distribution of the data. And it shows us where the central 50% of the values are. And then these two other whiskers are where 25% of the data lies out of it. And so box and whisker plots are a really quick way of visualizing data based off of the quartiles. And so if we draw this, we can see that we use the quartiles to make the ends, and then the whiskers go out to the mins and the max. Another type of data we can have are deciles, where we divide it into 10 equal parts, or even percentiles, where we divide it into 100 equal parts, and we talk about the percentage of data that comes across. And so if we get something that's in percentiles, which is common with ogives or ogives, we have the ability to talk about the 90th percentile, where 90% of the data comes before it. We see this a lot in scoring. And so when we break it down into percentiles, we can talk about the position of where a particular piece of data is, or how many other pieces of data are before it. So, scoring in the 90th percentile, 90% of the other data sets are below you, or you're beginning to be within the top 10% if we read it backwards. And so to calculate a percentile with a data entry, you take the number of data entries less than your particular value, and you divide it by the total number of entries. Sorry, I had the hiccups and I paused the audio, and I still have the hiccups. My apologies here. Have not been having good audio this week. Let's look at an example of calculating percentiles on this data set here. So we're going to look for the number that's 57,000, or the 57th 57. What we're going to do is we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 pieces of data. And so when we want to find the percentile that corresponds with a particular number, what we need to do is figure out how many data entries are less than 57, and then divide it by the total number of entries. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Yeah, so there's 25 data entries here. And before 57, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we have 15 entries before it. So let's use the calculation that we had received here. We have 15 entries less than 57, and we have 25 data entries. Let me clear this. Let's come back over here. We'll scroll down. So we want the percentile of 57. We found that there were 15 entries before 57 and a total of 25. And we'll multiply that by 100 to make it a percentage. So these are both divisible by 5. So that's 3/4. times 100%, or 75%. So 57,000 would be the 75th percentile for that particular data set. Did I do my calculation wrong? 5 goes into 15.3. Yes, I did. I did a quick bad math because I went in the calculator. 15 goes into 3, but it goes 5 there. This is why I should always check on the calculator. And 3 divided by 5 is 60. This is the 60th percentile. That looks better. 60th percentile. Glad I can double check my calculations. Now I'm going to peek. And I should have had my calculator out here. So let's move back down here. And so 15 divided by 25 is, 60 percentile. And again, Excel has the ability to do this for us. So if we come back to Excel and we can look at the data we have here, if we want to look at percentiles, let's say we want to find the percentile. So we use percentile X, and we're going to do the data range B12 or B2 to B16. And we can talk about the percentile in terms of what the percentage would be. And so this looks at it as a fraction. So 0.30 would be the 30th percentile. And that happens to fall on 26. If I come back up here and rechange the formula and say I wanted to look at the 60th percentile, well, that's where data 31 is from here. So we can push out particular percentiles using the percentile.exe function. In the comma here, we have to specify the percentile we're looking for. So if I wanted the 90th percentile out of this, we'll put 0.9. That falls in the middle here, somewhere between 38 and 39, and so it calculates it to be around 38.4. So Excel does give us the ability to calculate what number in our data falls within a percentile range. So we're able to use this both ways. And percentiles get used a lot. As I've said, we see it a lot in scores. We see it within medical data. What percentile of the population does a certain weight or height happen for a particular age? They're very common on baby charts and things as that. So percentiles are a good way of measuring where you are compared to all the other data sets, all the other pieces of data in the data set. All right, the last thing we're really going to talk about here is the standard score. And the standard score is we're going to call the Z value. Now, one of the things that happens is when we were able to find the standard deviation, it's measured in the same units as the variable and the mean. And so if we divide by this, we get something that's unitless. And a standard score is a really good way to talk about position across many given data sets. And so its calculation isn't too hard for us, too far away from us. We can look at the data value and we can subtract the mean and divide it by the standard deviation, all of which are very calculable in data that we had. But let's look at an example of this, and we'll come back and use this calculation. So we're going to use the data value minus the mean divided by the standard deviation. And let's look at how we can compare two distributions. So we have men's heights, which have a mean of 69.9 inches and a standard deviation of 3.0. Women's heights have a mean of 64.3 inches and a standard deviation of 2.6. So we can turn these into a z-score. And I will crack out my calculator here so I don't make a small calculation error on it. And because it determines z-scores talk about position in the data, we can use this position to kind of get a feeling for what the data means. So let's come over here, and we're gonna write our two data sets here. So we have that the mean height of men in inches is 69.9 inches with a standard deviation of 39 or 3.9 inches. 9 inches, or 3 inches, not 3.9. 69.9 and 3.0 inches. So 3.0. And we'll come over and we'll do the average, the mean height of women is 64.3. 64.3 inches with a standard deviation of 2.6 inches. And so if we have a data value of 6 feet, which is 72 inches, and in both groupings, well, I hope we could say that, 6 feet is tall, but how tall is it for men compared to women? And so we're comparing two data sets. Now, these data sets are very wide, and there's a diverse population in both of these sets, but they tend to follow a bell curve distribution. And so the mean for both sets is here. So if we convert to a z-score, so the z for a male will be 72 minus the mean, 69.9, divided by the 3.0. I will run to my calculator here. Like I said, I'm not going to make that same error that I did on the last slide. So 72 minus 69.9 divided by 3 is 0.7. And this is measuring in standard deviations. So if I were to go back to my bell curve, and knowing that I have the empirical rule, which says +1 standard deviation is here, 0.7 lies within 68% of all men. And so it's tall on the tall end, but it's not rare tall. It's within the 68%. Let's compare this to what a z-score will do when comparing a woman's height. So we'll do 64.3, because that's our, 72 is our data value. So 72 minus the 64.3 divided by 2.6. So I'll go to my calculator, 72 minus 64.3, and I'll divide the solution by 2.6, and that gives me about 2.96 as a standard deviation. So again, going back to our normal distribution, recognizing that 68% is between +1 and -1 standard deviation, the 3 standard deviations are out here. And so a 6-foot-tall woman ends up being removed and is rare compared to, 68% is here, and then we have 95, and so from here to here is 99.7% of the data. And so this is a rare percentage of the overall calculated height in women. And so if we compare these two numbers, the larger the z-score is in absolute value, the further away it is from the mean for that group. And this gives an idea of how we can compare two data sets, even though they might look the same. 72 inches is the same height. In how the distribution for the data falls, the standard score, or the z-score, gives us a way of comparing. Just like the CV, or the coefficient of variation, did a similar thing. Here we can look at the rarity of a piece of data by noting its position. And so the z-score becomes a very good way to talk about position within the normal distribution. And this we see coming across. And so what the book says is unusual scores are 2 or greater, very unusual scores are 3 or greater. And it falls with how these things get distributed. And that wraps up chapter 2. I'm going to do a short video on ethics, which is out of the textbook. It's what's on the syllabus for this week. And then we're going to be looking at, or part of the assignments that we have coming out of this week will be for looking at our project, and our project is really going to be Excel based. It's going to be taking all the information that we have here. And so that a project is kind of a set of things to do on some given data in Excel, and that'll be due in about 2 weeks coming across. So this gets us through chapter 2. I will give a warning that we change gears very strongly in going into chapter 3, that we stop looking at statistics for a bit and we start talking about probability. So try to get comfortable with the homework for chapter 2. Bring me questions. Please use Excel as your calculator as much as possible. We'll find that will make it easier for us to build things out of this.